My name is Michael Kokinderfer, and I'll be talking about automated decision-making for safety critical systems. Now, much of the focus and advances of AI have involved applications where it has been okay to occasionally make mistakes, like accidentally recommending the wrong movie or misclassifying a dog as a cat. For many years, work on AI has focused on algorithms for making these AI systems better, which is great, and there is still a ways to go. Not too long ago, the focus turned to large data sets with the hope that large data sets will continue to improve the performance of our systems. Now, the focus is starting to turn to the challenge of validation. There is a growing realization that maybe the hard part in AI is not really the building of the algorithms or collecting of the data, but rather it is making sure that the system will behave the way we want when deployed in the real world. After a series of embarrassments, massive research efforts are underway to validate the fairness of AI systems and reducing various forms of bias and discrimination that may be difficult to predict during the design phase of these AI systems, and that only really become apparent when deployed in the real world. These are costly mistakes, costly in terms of cost to society, cost to societal trust, costly in terms of the reputations of the companies that use and deploy these systems. I'm an aerospace professor. In this industry, we try to build highly reliable systems that take people into outer space and fly the 4.5 billion passengers in 2019 around the world. That number, of course, went down in 2020. Aerospace systems are incredibly complex, yet an incredibly safe place to be nowadays is in a metal tube at 30,000 feet. As all the faculty in my department can tell you, the future of aerospace is autonomy, where greater levels of autonomy can enable greater flexibility in the exploration of distant planets, or safer, more efficient, and more sustainable aviation to transport passengers and goods. In this talk, I'll discuss some of our work on validating complex decision-making systems. As most of you know, there are different ways to model decision-making problems. There's the Markov decision process where we capture outcome uncertainty. Then there are the partially observable Markov decision processes, or POMDPs, where we capture state uncertainty. This model is especially relevant in aerospace contexts where we need to be robust to sensor errors, occlusions, and so forth. There's also reinforcement learning where we don't know the state transition probabilities or rewards ahead of time and have to interact with the environment to understand how it works. POMDPs are especially relevant to safety critical systems where we need to provide robustness to various sources of uncertainty. Unfortunately, many of the algorithms for solving POMDPs are extremely complicated. There were some tools available at the time that allowed you to specify problems using text files containing transition probabilities, reward parameters, and so forth. But for many of the problems of interest, even just the transition probabilities would be too large to fit in a file. We wanted to create a library that would allow non-expert users to specify their problems programmatically. So one of the first activities of my graduate students at Stanford was to create a library that would make it easy for people from different disciplines to specify their problems and then try out different solution algorithms. We wanted something that would be fast and easy to use, as well as usable for teaching. This resulted in POMDPs.jl, which is written in the divine language, that is Julia. It's interactive, it's fast, it's typed, and we can write for loops and do branching without a huge performance penalty. To make many of these ideas accessible, I wrote Decision Making Under Uncertainty that came out from MIT Press in 2015. It was targeted at a general engineering audience. Many of the ideas came from the AI community, of course, though many of those ideas originated in the operations research community a few decades previously. Many of the algorithms for decision-making under uncertainty is fundamentally a form of optimization. And it turns out that the validation of decision-making and other forms of AI systems can also be framed as optimization problems. I found that many people, both within the AI community and outside, were limited in terms of their breadth of exposure to optimization algorithms. So together with my former PhD student, Tim Wheeler, we wrote a textbook that came out in 2019 on optimization. Instead of pseudocode, we used actual executable Julia code to elaborate on the algorithms while still preserving human readability. I'm really excited about a new book that we're wrapping up right now. It's titled Algorithms for Decision Making, together with Tim Wheeler and Kyle Ray. You can find the PDF on algorithmsbook.com. In its 700 pages, we discuss the various sources of uncertainty and the challenges they present to making robust decisions, including outcome uncertainty, model uncertainty, state uncertainty, and interaction uncertainty. That is the uncertainty that arises from multiple agents interacting with each other. Again, we provide implementations of the algorithms in Julia. As you can see, we were inspired by the format of Edward Tufte's books. A major success story of a POMDP approach to modeling decision problems is ACAS X, the next generation aircraft collision avoidance system. It grew out of our research back when I was at MIT Lincoln Laboratory. It started out as a concept on a whiteboard in 2007, and we were able to sketch out much of the details of the decision-making logic over a couple of years, resulting in a technical report in 2011. You can find a PDF of it online. But it wasn't until 2018, after tremendous effort by folks at the FAA, Lincoln Laboratory, Johns Hopkins Applied Physics Laboratory, the MITRE Corporation, and others, that it became an international standard, RTCA DO385. That's the version for manned aircraft. The version for unmanned aircraft was accepted as a standard just in 2020. So you might be wondering why it took so long to have it accepted as an international standard, despite teams working on it spanning multiple organizations. Well, this is a system that we don't want to mess up, and it is a system that everyone in the world needs to agree upon. There was quite a bit of interest in collision avoidance long before 2007. In fact, in 1956, there was a mid-air collision over the Grand Canyon involving United Airlines and TWA. There were 128 fatalities, a press frenzy, congressional hearings, and ultimately the establishment of the FAA in 1958. Even with the ground-based radars and air traffic control, there were still these mid-air collisions. The one on the left was actually captured on film as it happened in 1978. There were 144 fatalities, and it spurred additional interest in developing a system that was later called TCAS, the Traffic Alert and Collision Avoidance System. It wasn't until after the 1986 collision over Cerritos, California, a few miles from Disneyland, that Congress decided to put laws into effect that would mandate the equipage of TCAS in the US. By around the year 2000, the rest of the world has fallen suit. TCAS is composed of a surveillance system that detects and tracks intruders. It passes these sensor measurements onto the advisory logic that decides whether to provide an alert to the pilots and which maneuver to advise. These resolution advisories are passed on to the pilots in the cockpit. The advisory logic contains a bunch of if-then rules, different parameters, and so forth. So maybe you can guess as to how many pages of pseudocode is required to specify this logic. Before I tell you, I'll just say I'm a third-generation pilot. My dad ran a flight school and his dad ran a flight school, but even so, I didn't properly appreciate the complexity of getting this logic right. I want to show you something that I found a couple of years ago on Instagram. So someone on Instagram posted something that says they use coding and algorithms so the drones didn't crash into each other. And then someone wrote, if going to crash into each other, don't. And then someone who's lying about at least one thing says, as a robotics major, I can confirm this is 100% how coding works. And so there is a general lack of appreciation by the general public, and perhaps also us as engineers, in the complexity of getting this right. This is a screenshot of Volume 1 of RTCA DO185B, the TCAS standard. The first volume has 1,799 pages, and 440 of it is pseudocode. I got to know many of the brilliant people who worked on this system. Some of them had worked on it from before I was born. It placed a huge burden on the designers to anticipate all the various edge cases and decide on a way to resolve them. It required a massive engineering effort. Consequently, TCAS has been a major success story. Since TCAS was mandated in the US on large aircraft, there have been exactly 0 mid-air collisions involving TCAS. Smaller general aviation aircraft, like the ones I use to fly, are not equipped with TCAS, and there have been several mid-air collisions every year just in the United States. So when we were designing the next generation of this system, I spent a while thinking about what are the major challenges in building a reliable system. And it really boils down to these 3 challenges. The first one is state uncertainty. We have imperfect sensors. We also have dynamic uncertainty. Most of the time aircraft fly straight, but they might turn left or right with some probability. The other challenge is that there are multiple competing objectives. The system has to very carefully balance both safety and operational considerations. And getting this balance right is extremely difficult. And it turns out that, of course, these 3 challenges can be framed in terms of the POMDP framework. And we can use dynamic programming to find an approximate solution. I'd like to show you a plot of the policy that resulted from optimizing one of our first models when we first started working on this line of research. The horizontal axis here is the time to potential collision, and the vertical axis is our altitude relative to the intruder. This intruder stays fixed at 0, 0. This is a slice through this state space, a higher dimensional state space, under the assumption that we have not yet issued an advisory and both our aircraft and the intruder aircraft are currently level. What you'll notice here is that there's a little notch on the left-hand side. So why is that? Actually, at first, we thought this could be a bug in our implementation. And it turns out that if you fill in that gap, you actually do worse. So the reason for this is you're able to lower the alert rate a bit when you delay your alert when you're roughly co-altitude. It's possible that the intruder might just move out of the way and you can lower your alert rate, which is a very important operational metric. Another metric that it helps with is the reversal rate. So TCAS and ACAS X, it allows you to reverse the direction of the aircraft. So let's say initially you issue a climb, you can later reverse the climb to a descent. So if you delay your alert a little bit, if you're roughly co-altitude, it reduces the likelihood that you commit to a direction that you later have to reverse. And this brings us to another reason, perhaps one of the most important metrics, which is safety. Now, because aircraft are physically constrained, it takes a while for the aircraft to change direction. And if you do a reversal, it eats up quite a bit of time as the aircraft are converging upon each other. Another interesting feature here is that you don't alert at all when you're within 5 seconds of collision. Now, this is because we carried over an assumption inherent in TCAS that it takes the pilots exactly 5 seconds to respond to their advisory. Since we're modeling this problem as a POMDP and there's a cost for alerting, it doesn't want to accrue the cost of alerting you to a potential collision when it makes no difference in terms of the trajectories of the aircraft. So what we did was we ran 1 million stressing encounters. I should emphasize that these are stressing encounters, not meant to be representative of the actual airspace. And what we found is that the number of near midair collisions, or NMAX, was greatly reduced in this early prototype by a factor of 50. The number of alerts were reduced by 30%. While the number of strengthenings increased by more than a factor of 2. So that's not great. A strengthening is when you increase the vertical rate of the aircraft. after an initial advisory. However, we see that the number of reversals are significantly decreased. So overall, this is a great story, but if we wanted to reduce the rate of strengthenings, then what would we do? Well, we would perhaps increase the cost of strengthening and re-optimize. And this will be at the expense of some of these other metrics. But the key innovation here is that it moves the burden on the engineers from trying to design pseudocode to directing much more of their focus on the balancing of these different metrics. So Monte Carlo analysis can go a long way in validating a system. We're interested, of course, in estimating the probability of a failure. This is difficult for a number of reasons. One is that we need to run this in simulation, and we need a good model of the environment. An underappreciated fact is that this model absolutely must be independent of the model used for optimizing the logic. For ACAS X, we used a relatively simple POMDP model, but we used a much higher fidelity model for the validation of the resulting policy. We collected 9 months of radar data from all of the FAA and Department of Defense radars and built up a Bayesian network to capture all the various statistical correlations between the various variables. Then we can sample from that many times and arrive at a probability of collision. Since our systems are very safe, we naturally need many simulations in order to arrive at a good failure probability estimate. We can take advantage of importance sampling and the cross-entropy method to reduce the variance of our estimates, but we still need quite a bit of computation. During the validation of ACAS X, we ran tens of billions of simulations, and we were one of the primary users of the Lincoln Laboratory supercomputing grid. At design time, we also want to be able to identify the most likely failure modes. We, of course, need a probabilistic model of the environment in order to measure likelihood. Searching the space of possible scenarios is also challenging because there are many variables and the scenarios extend across in time. I'll dig more deeply into this shortly. When we throw massive compute power at simulating many simulations, we will, of course, find failures. At least for aircraft collision avoidance systems, and this goes for automated driving as well, no system will be perfectly safe. If our simulations discover hundreds of failure scenarios, we'd like to categorize them into failure modes that are interpretable. Then we can decide what to do about those failure modes. Identifying the most likely failure can actually be framed as an optimization problem where we try to maximize the probability of a trajectory subject to failure. The key insight here is that this optimization problem can be framed as a POMDP, and we can use different POMDP solution techniques to arrive at a failure. We call this methodology adaptive stress testing, and it works like this. We have a simulator that we can step forward in time. It encapsulates an environment and the system under test. So that system under test, we just need to be able to execute it. So we don't need the source code, we just need to be able to execute it. So it makes it very easy to try out different systems like ACAS X and TCAS and automated driving systems and flight management systems and so forth. The output of the simulator is an observation and reward. The reward is related to the log probability of the transition in the environment. Now, in a POMDP, of course, we want to maximize the sum of rewards. When we're maximizing the sum of log probabilities, we're actually maximizing the likelihood of a trajectory. Okay. So this gets fed into a reinforcement learner that outputs actions. The actions represent disturbances to the environment. It turns out we can use any reinforcement learner we want. We can use Monte Carlo tree search or deep reinforcement learning or whatever. And the aim is to just output the most likely failure path. This is an example failure from a very early prototype of ACAS X. And it's really nice. We get these trajectories. On the left, we see a plot of the lateral motion of the aircraft with the different advisories indicated. And on the right-hand side, we see the vertical profile of this encounter with the different advisories. This one actually led to a collision. Now, understanding these kinds of failures at design time it's extremely useful. So with the success of the application of adaptive stress testing to ACAS X, my students were interested in seeing how well it scales to automated driving problems. And this is a simulation in the open source Carless simulator. We're simulating a driving policy as well as a perceptual system. You can see the bounding box around a pedestrian. What we find is that the most likely failure is not very relevant to us. Okay, the pedestrian is basically running at our vehicle and flinging themselves on the hood. So this is not very relevant because we are not at fault. So it turns out that we can actually incorporate into the reward function the notion of fault. And to do this, my student Anthony Corso implemented the RSS system from Mobileye, just based on a white paper that was posted on arXiv. What we get as the most likely at-fault failure is much more interesting. We see that the bounding box is bouncing around. This is due to perceptual errors. And we also see that our car is driving a little bit more aggressively than perhaps we would like to see when a pedestrian is starting to wander into the road. So understanding this at design time is very important because it may lead us to decide to add additional sensors or change parameters in our perceptual system, maybe changing some of the parameters in our particle filter or Kalman filter. And we might also want to play with the tuning of the aggressiveness of the vehicle. Adaptive stress testing is a sampling-based method. Regardless of whether we use Monte Carlo tree search or deep reinforcement learning in our optimization loop, we do not arrive at any formal guarantees. We have also explored the use of formal methods for verification, which do allow us to make formal guarantees about performance, at least guarantees with respect to some model. A collaboration with others in the Stanford Computer Science Department a few years ago led to the creation of the ReLUplex algorithm, which is a sound and complete algorithm for verifying properties of neural networks. The properties are defined over a continuum of inputs, and so there is not a way to exhaustively enumerate all of those inputs and manually check that the outputs adhere to the specified property. It actually involves formally reasoning about the individual weights in the neural network and arriving at a proof that the property holds, or if it doesn't, it will produce a counterexample. We can use verification algorithms to support reachability analysis, as I'll discuss shortly. We may want to prove that if we follow a policy represented by a neural network, that it is impossible to enter an unsafe set. We have also done work on probabilistic model checking, where instead of determining whether a property holds or not, we can prove that a property holds with at least some probability. What initiated our work on ReLUplex was some work done by my former student Kyle Julian. We were interested in seeing whether we could compress policies for unmanned aircraft collision avoidance represented as numerical lookup tables. What I'm showing here is just a notional policy that was generated using an open source implementation of a toy collision avoidance problem, not the official ACAS X system, of course. This table occupied 1.22 gigabytes, and he was able to fit a neural network to the action value function, which resulted in a policy that looks like what you see on the right. Instead of 1.22 gigabytes, the weights in the neural network occupy only 103 kilobytes, which is quite an impressive compression ratio. He didn't spend too long training the network, and as you can see, the decision boundaries are not perfect, but it looks roughly sensible. But what was surprising about this research, which you can read about in the journal article below, is that it performs super well when evaluated on a variety of metrics using Monte Carlo simulation. Of course, one should be very wary of using a neural network for a safety critical system. And the reason for that is that neural networks can produce unreasonable outputs for what appear to be benign inputs, as we have seen in the literature on adversarial examples in image classification. So we wanted to see whether there was something formal that we could say about the properties of these learned networks. One property that we might want to prove is that regions where we expect one type of advisory provide that advisory consistently over the infinitely many points that compose that region. Here in our plot, it looks like we consistently produce a descend 1500 advisory in that top rectangle. But of course, the image we see is produced only by a finite sampling of those points in the rectangle. But ReLUplex is able to verify that this property holds. There are plenty of other kinds of properties that we might also like to prove. We found that proving properties like these can take on the order of minutes. That is for networks of the size relevant to collision avoidance. Unfortunately, ReLUplex doesn't scale up to networks of the size used for solving image classification tasks. However, there has been quite a bit of follow-up work on improving the efficiency of ReLUplex, leading to the open source release of the Marabou framework. It scales better to larger networks, but we still can't prove properties about networks with hundreds of thousands of units. Many other labs around the world have also made progress in the past few years in developing verification algorithms. My former postdoc, Chonglu Liu, who is now a professor at CMU, went through and surveyed all of these different neural verification algorithms, and we produced a Julia library and a rather long survey article. These algorithms combine insights from reachability analysis, primal and dual optimization, and search algorithms. Some of these algorithms sacrifice completeness in order to achieve greater levels of scalability. We can use these neural network verification algorithms to do some reachability analysis to prove, for an example, that if we follow the advisories given by the neural network, that we'll always be safe. The first step here is to discretize the state space using a grid. To illustrate this process, let's say we are in the cell that I highlighted in red here. It looks like the two actions that are available here are either descend or climb 1500 feet per minute. But we can call out to one of these neural network verifiers to actually prove that that is indeed the case. As I've indicated here, this is indeed the case. What we can do is simulate the dynamics forward using an over-approximation conditioned on the various actions. In this case, we're simulating descend 1500 forward, and we are guaranteed to end up somewhere within these two cells. We can also simulate a climb, and we end up in those cells. From those cells, we can look at where we might end up. We've applied this technique to study reachability for both vertical avoidance maneuvers as well as horizontal avoidance maneuvers. This is an example of a horizontal avoidance maneuver. What we want to show is that the intruder aircraft cannot come within a certain threshold of us if we follow our advisories. My student Chelsea Sidrain has been leading some work on symbolic methods for closed-loop reachability analysis that does not require discretization and may be more scalable to larger problems. Together with a former postdoc of mine, they created a tool that provides relational piecewise linear over-approximations of multidimensional functions. This over-approximation can be used to represent the dynamics of the system. The example here is of the inverted pendulum. We start in some initial region designated by that square at the bottom left of the state space. What we would like to determine is what region we might end up in after 10 time steps. One approach, of course, is to run a bunch of simulations with our neural network policy in the loop, and we see that we end up in that orange region. Of course, we don't have any guarantees, but that's roughly where we will end up. Another approach is to use a mixed integer problem formulation and use an off-the-shelf solver to determine the rectangle we will be in at each step, and then just iterate a few times. This approach is called concrete reachability because we make the reachable set concrete after each step. Another approach is to use what is called symbolic reachability, which results in a larger mixed integer program that takes longer to solve, but it can result in a tighter bound for where the pendulum might be after 10 steps. I'd like to briefly highlight some of the work that my student Kyle did on TaxiNet. So TaxiNet is a neural network that has been trained to follow the center line of a runway or a taxiway. And what we want to do is figure out whether image errors can make the aircraft depart the runway or the taxiway. This is done in the X-plane simulator, which is a photorealistic aircraft simulator. The camera is mounted on the side of the aircraft, and we want to translate those images into steering commands. So we take as input the image, we downsample it. That image, the downsampled image, is then passed into the neural network. The neural network outputs predictions of cross-track error as well as heading error. And then from those two quantities, those are fed into a simple linear controller that outputs rudder or nose wheel commands. And this then gets updated in the simulator. So before we started using our neural network verification tools, we started playing with different lighting conditions, ranging from clear days to overcast days. And what we saw was that the neural networks actually seemed to perform extremely well. We wanted to see what would happen if we allowed up to 3% perturbation of the input image to the system and see if those perturbed images could get the aircraft off the left side of the runway. So we actually made a series of calls out to Marabou to find the perturbation that would lead to the most extreme left steering command. As I run this video, you can see the trajectory evolve on the bottom left together with the true image, the downsampled image, and the perturbed image. The perturbed image looks relatively benign. As you can see, we can get the aircraft pretty far to the left side of the runway. However, there comes a point where no allowed perturbation prevents it from correcting itself. So this approach failed to find a failure trajectory. The problem with the previous approach is that we were only optimizing for extreme left steering commands. The key insight that Kyle had was to not constrain ourselves to extreme left steering, but rather allow for both extreme left and right steering, and then use adaptive stress testing to find the right sequence of image perturbations that would result in a failure. In these series of plots, you can see the results of our Monte Carlo tree search tree, with the nodes shown in red, with the final output of the adaptive stress testing shown in blue. With 2% perturbation, adaptive stress testing didn't find a failure. But with 3% perturbation, we were able to find a very fascinating failure. Here we have a series of perturbations that lead to left steering commands that bring the aircraft close to the left side of the runway. Then we produce a series of perturbations that lead to right steering commands. The neural network finds itself in a situation that is quite different from the examples it was trained on, and it does not know how to recover. Here are some plots for 3.5% perturbation and 4% perturbations. When we go up to 4%, then we can actually get the aircraft to just go off the side of the runway. I should emphasize here that adaptive stress testing on its own would not have been able to find these failures. If we just do adaptive stress testing with random image perturbations, no failures result. The success of this verification method is in the ability of Marabou to find adversarial image examples, combined with the ability of adaptive stress testing to search through a sequence of actions, bringing it closer to a failure. We can actually find more likely failures if we allow Marabou to search with different amounts of image perturbation. Adaptive stress testing can find the right sequence of image perturbation levels that not only leads to a failure, but also maximizes the likelihood of failure. We don't have a good model of perception likelihood, but we can say that less image perturbation is more likely than more image perturbation. So we played with different perturbation levels and looked at the mean perturbation amount. We started to notice that adaptive stress testing would time the crossing of the runway center line to correspond to gaps between the dash center line. The idea being that it is easier to fold the neural network if there is less guidance from the center line. I'd also like to quickly mention some work that my former student Maxime Bouton did on probabilistic model checking. The idea in probabilistic model checking is that you check whether some property holds with some probability. This probability can be specified in some language like LTL or linear temporal logic. There are many great tools for probabilistic model checking, but they generally assume full state observability. There was one exception elaborated in a 2017 paper that involved partial observability, but the approach they took was to discretize the belief space and turn it into a fully observed problem. Now, of course, this will not scale very well at all. So what Maxime did was to interface with a library that converts LTL formulas into finite state machines. Then he wrote a little bit of code that combines that finite state machine with a POMDP representation of the problem. This allows us to use POMDPs.jl to solve for policies that maximize the probability of these LTL properties, and it also tells us the probability of satisfaction. You can find our implementation online. Led by my student Sydney Katz, we have also started to look at using probabilistic model checking to provide probabilistic safety guarantees when using a neural network controller. Instead of using a uniform discretization of the state space like what Kyle did for his reachability analysis, she developed an adaptive discretization method that minimizes the volume of the input space covered by cells with multiple different actions recommended by the neural network policy. The number of actions available from a cell can be determined by calls to Marabou. We can then use this over approximation to arrive at a failure probability estimate from different points in the state space. We have to be careful about how we do this since we want to preserve the formal guarantee that we want from a probabilistic model checker, that probability of failure is guaranteed to not exceed some threshold. Anyway, Sydney came up with some methods to provide variable levels of refinement of these probabilistic guarantees inspired by some state abstraction methods discussed in the reinforcement learning literature. With additional computational time, we can afford to prove that we are safe in certain areas of the state space that we would not have been able to prove before. When we are building safety critical systems, or actually any kind of decision making or decision support system, we want to make sure that the system is robust to the various sources of uncertainty inherent in the real world. A POMDP is one way to frame this kind of uncertainty, and we can use a variety of different optimization algorithms for solving them or approximating their solutions. This optimization can improve robustness in ways that are sometimes counterintuitive. We saw this with aircraft collision avoidance, and this is where these kinds of techniques can bring quite a bit of value. However, proper validation of the system is absolutely critical. Establishing trust in safety critical systems requires a variety of different approaches, including identifying and categorizing failure modes. There is no silver bullet here. Formal methods have difficulty scaling to problems of interest, and sampling-based approaches on their own can have difficulty finding relevant failures. There are some very exciting applications of formal methods that can support the validation of controllers represented by neural networks. We'll have to see how far we can take them. These are still very early days. You can find my email at the bottom of the slide, as well as a link to the webpage of the Stanford Intelligent Systems Laboratory.